Hello everyone, this is Boxiang Wang. I'm delighted to present our work named by Tesseract, Parallelize the Tensor Parallelism Efficiently. The presentation consists of 4 parts: introduction and motivation, methodology of this work named as Tesseract, experiments, and the conclusion. Together with the improvements in state-of-the-art accuracies of various tasks, deep learning models are getting significantly larger. However, it is extremely difficult to implement these large models because limited GPU memory makes it impossible to fit large models into a single GPU or even a GPU server. In recent years, with the rapid development speed of novel transformer models, this situation has become more serious. Model sizes evolve tens or even hundreds of times in 18 months. While in contrast, GPU memory size increases with only a speed of 1.7 times every 18 months currently. We could find that the growing gap between demand and supply is getting bigger, and it will get worse and worse. In this situation, it becomes necessary to introduce parallel processing and distributed learning methods into state-of-the-art deep learning model training and inference. There are 3 different parallelisms widely used in today's machine learning systems: data parallelism, pipeline parallelism, and tensor parallelism. For data parallelism, it distributes data used across processors. These distributed data will be processed in parallel, and the model parameters will be updated synchronously. In data parallelism, communications happen at all reduced operations to sum the gradients from all processors. For pipeline parallelism, it splits the model by layer. Data is split into macro batches for pipelining. In pipeline parallelism, communications occur between pipeline stages. For tensor parallelism, tensors for matrix multiplications are split across devices. Each device conducts part of the matrix multiplication. In tensor parallelism, communications happen during the matrix multiplication procedure. For our work, Tesseract, it focuses on tensor parallelism with huge transformer-like models. I will shortly introduce transformer here first. Transformer, introduced by the paper "Attention is All You Need," has been proved to be effective among various tasks like computer vision and natural language processing. It is right now the most popular mechanism in deep learning area, and it has many gigantic variations. For example, GPT-3 and Wudao, which has 1.75 trillion parameters. The original transformer consists of encoders and decoders. Encoders and decoders are again composed of multi-head attention and feed-forward layers. The multi-head attention module mentioned above first uses a linear layer to project the original hidden vectors into query, keys, and value matrices, also known as Q, K, and Y matrices. Multi-head attention is calculated as this function. It is query multiply the transposed key matrix and divided by the root of query's matrix dimension. After applying a softmax activation function, multiply the value matrix. Previous tensor parallelism solutions includes Megatron LM. It introduced a 1D distributed method to speed up the training process of huge transformer models. Its solution is described as the picture shown. Megatron's 1D solution splits 2 different parameter matrices in 2 different directions. By conducting matrix multiplication accordingly, Megatron adds 2 different results matrices together to get the final result. For Megatron, when the number of processors increases, the communication required will also increase greatly. which makes it inefficient. In this situation, we introduce Tesseract to reduce communications required when dealing with matrix multiplication. This picture illustrates how Tesseract arranges processors. For a total of P processors, Tesseract arranged them with a shape of Q times D, where D is the Tesseract depth and P is Tesseract dimension. We can call processors that with the same depth a layer. Here we illustrate methods to split input matrices A and B and method to combine output matrix C, assuming processor's shape Q equals to 2, D equals to 2. The blue region representing a layer among the processors with a shape of Q equals to 2. The first part represents matrix A with shape AB will be split into D times Q squared partition matrices, each with shape of A divided by QD and B divided by Q. The second part represents matrix B with shape BC will be split into Q squared partition matrices with shape of B divided by Q, C divided by Q. Partition matrices will be stored in each layer. The third part represents D times Q squared partition matrices with shape of A divided by QD, C divided by Q will be combined into matrix C with shape AC. In algorithm, Tesseract's matrix multiplication takes input matrix A with a size of AB and a matrix B with size BC, and the supposed output is matrix C with the shape of AC. First, Tesseract partition A and B as mentioned before, then we store all the partition matrices resulted from A and B into processor IJK accordingly, and Cijk equals to 0 will be also stored into processor IJK accordingly. For each IJK, we store Bij, AHJ, and CHJ, which equals to 0 into each processor IJK, where K could be different, and H equals to I plus K times Q. Then for each IJK, and T from 0 to Q minus 1, we broadcast a ITK along its column and broadcast PTJK along its row. On each processor, say IJK equals to its previous value at AITK multiply BTJK. Finally, Tesseract combine all the Cijk accordingly to get the final result, matrix C. This slide illustrates the specific transformer operation of Tesseract. B stands for batch size, S stands for sequence length, H stands for hidden size, N stands for number of heads, Q stands for Tesseract dimension, and D stands for Tesseract depth. In this example, we used Q equals to 2 and D equals to 2 for presentation. For feed-forward operation, input matrix with the shape of BH is split into partitions of B divided by DQ, H divided by Q. Two parameter matrices with size of H 4H and 4HH will be split into size of H divided by Q, 4H divided by Q, and 4H divided by Q, H divided by Q, respectively. Tesseract multiply input matrix and two different parameter matrices accordingly and get the final output matrix. For multi-head attention operation, input matrix is split in the same manner. It then multiply a partition parameter matrix with a shape of H divided by Q, 3H divided by Q for attention calculation. After obtaining the QK weight matrices, we apply attention to them, which is Q multiplied transposed K divided by root of key matrix dimension to set the variance of qk to 1. After applying softmax activation function, multiply the result to v, and finally multiply another parameter matrix to get the output matrix. Tesseract, as a novel structure of tensor parallelism, is capable to implement existing data parallelism and Papillon parallelism as well. To further enhance its performance, as shown in this slide, it demonstrates the distribution of GPUs with the data parallel size equals to 2, Papillon parallel size equals to 2, Tesseract dimension equals to 2, and depth equals to 2. The number of total GPU involved will be 32 equals to data parallel size times Papillon parallel size times depth times square of dimension, where Tesseract depth times square of Tesseract dimension is Tesseract size. So in this picture, blocks in the same color represent GPUs in the same Tesseract module. About the experiments, our experiments are conducted on the Malucina server. On this supercomputer, there are 200 GPU nodes with 4 NVIDIA A100 GPUs per node. Our experiments are conducted with 1, 2, 4, 8, and 16 nodes accordingly, and the number of GPUs ranging from 1 to 64. With different settings, strong scaling and weak scaling settings were applied to this experiment. Besides, all the experiment results are the averages of 20 times of the same experiments in this section. In the strong scaling setting experiments, as shown in the table, we fix the problem size. The batch size is set as 12, the hidden set is set as 3072, and the number of attention heads is fixed at 62 due to the limitation of memory on each processor. From the results of the experiments, it manifests that with the same Tesseract dimension, greater Tesseract depths will reduce the forward and backward time per batch size, but not in inverse proportion, since the communication loss will also increase. Besides, from the example between q equals to 4, d equals to 4, and q equals to 8, d equals to 1 arrangements, with the same number of processors, greater Tesseract depths could lead to less forward and backward time. In the first situation, due to the increment of communication cost, double the depths could not result in a half forward-backward time, while the outcome of the experiment in strong scaling between q equals to 4, d equals to 4 arrangement and q equals to 8, d equals to 1 arrangement could be because of the high communication loss, as the latter arrangement is supposed to have smaller matrices to compute. According to the table, from the results of Tesseract with q equals to 4, we could find out that compared with Tesseract setting with a depth of 1, Tesseract with a depth larger than 1 could outperform by a large margin. Besides, when using the same amount of GPU, for example 64, our Tesseract in the shape of q equals to 4, d equals to 4 has a huge speedup compared with a 2D solution with a shape of q equals to 1, d equals to 1 calculated as 2.07. This could help to prove that with larger depths at the same amount of processors, the distributed language model will have higher efficiency. Besides the comparison between the Tesseract with different depth settings, we can also calculate the speedup of Tesseract between Megatron and Optimus. Here we focus on the experiments with 64 GPUs in the different parallelization structures compared to Megatron. Compared to Megatron, our Tesseract reached a speedup of 1.37. Compared to Optimus, our work reached a speedup of 1.53. In the weak scaling setting experiments, the parameter setting depends on the individual arrangement of GPUs in order to allocate the same problem size on each GPU. As shown in the table, for all three different structures, we set the corresponding hidden size and number of attention heads to get a fixed size of input parameters. And the setting confirms batch size divided by dimension times depth equals to 48, and number of attention heads divided by dimension equals to 16, and hidden size divided by number of attention heads equals to 192, due to the memory of each GPU used. From the comparison between settings of Q equals to 4, D equals to 4, and Q equals to 8, D equals to 1, with the same amount of total processors, we could come up with the enhancement of efficiency. This proves that with bigger depths and the same amount of processors, the distributed language model will have higher efficiency. Throughput is calculated as the ratio of the batch size to the sum of forward and backward time per iteration. And inference is the ratio of batch size to the sum of forward time per iteration only. For this weak scaling setting experiment, the memory used for each GPU is the same, but the communications required between GPUs are different. Thus, the throughput and inference speed are naturally faster for experiments with fewer GPU used. For this reason, we compared the results using the same amount of GPUs instead. From our experiments results, it shows that Tesseract reaches a maximum of 3.37 times the throughput compared to Megatron and 1.71 times the throughput compared to Optimus in the setting of 64 total GPUs. For inference, Tesseract reached a maximum of 4.01 times the inference compared to Megatron and 1.69 times the inference compared to Optimus. This result supports that our Tesseract provide better utilization of GPU server compared to other tensor parallelism. For the comparison between Tesseract Q equals to 4, D equals to 4, and Q equals to 8, D equals to 1 settings, which both used 64 GPUs in total, we find that by offering a bigger depth on Tesseract, the communication required is reduced significantly. For throughput, Q equals to 4, D equals to 4 achieves 1.51 times compared to Q equals to 8, D equals to 1, and 1.55 times inference. Besides, we have also conducted convergence experiments with Gaussian transformer. Tesseract does not introduce any approximations, thus it does not affect the training accuracy for neural networks. As shown in the figure, we compared the accuracy results of a Gaussian transformer model with the same parameter settings on different GPU. Besides, we have also conducted convergence experiments with Gaussian transformer. Tesseract does not introduce any approximations, thus it does not affect the training accuracy for neural networks. As shown in the figure, we compared the accuracy results of a Gaussian transformer model with the same parameters on different GPU settings. In this Gaussian transformer model, the number of epochs is 300, batch size is 512, Atom is used as the optimizer, and the learning rate is 0.003 with a weight decay of 0.3. To control the variables, we fixed random seeds and initialization methods for this experiment. The training dataset is ImageNet 100 according to our accuracy results. Tesseract does not affect the model accuracy. In conclusion, we designed a further parallelized tensor parallelism structure, Tesseract, and we tested this work on the computer vision model Gaussian transformer and language model transformer. By using Tesseract, we reached the speedups compared to other tensor parallelism structures on deep learning models. Besides, compared to previous tensor parallelisms, our work requires less memory on each GPU because of its tensor split method, and it requires less communication cost, which in return led to higher efficiency. And in the end, thank you for your time for this presentation.